In example 2, we need to evaluate the following limits. And we're going to try to evaluate these algebraically, and we can also take a look at some of them if we need to graphically. With this first one, we've got the limit as x approaches 2. You want to look at these rational functions, and you want to see what values, or for what values, the function is discontinuous. So we know that x plus 3 cannot be 0, so x cannot be negative 3. The numerator can't be factored, and so this value is definitely a vertical asymptote, but by any means it is a discontinuity. The function is not continuous at this value, x is equal to negative 3. Well, hey, lucky for us, we are not asked to evaluate the limit as x approaches negative 3. We're asked to evaluate the limit as x approaches 2. So at this stage of the game, when you've excluded any discontinuities from these values, or this value of x I should say, we can do some direct substitution. So the limit as x approaches 2 is going to be equal to 2 squared minus 5 over 2 plus 3. And if I do my math correctly, I think this is 4 minus 5, or negative 1. And then we've got 2 plus 3, or 5 in the bottom. You could verify this graphically. You could also verify this numerically if you wanted to. You want to start to try to move, though, towards being able to do these algebraically if possible. If we can do these algebraically, we can find the exact result. Whereas if we look at a graph, sometimes the graph can be a little misleading. It's a great spot to start. If you're not understanding what the value is approaching, start there. Start looking at a graph. Take a look at the table, see what's going on. The next one, we're asked to evaluate this function for a value of negative 4. Excuse me, we're not asked to evaluate this function at negative 4. We're asked to find the limit as x approaches negative 4. Let's see if we can use direct substitution or evaluation here with this one. If we take a look at the bottom, we know that x squared plus 2x minus 8 cannot be 0. Solving this, we could factor. X plus 4, x minus 2 cannot be 0. So x cannot be negative 4 or 2. The reason why we're taking a look at those values is this function is not continuous at negative 4. If we take a look to see what kind of discontinuity that is, that actually might help us to solve this limit problem. One of the things you can try with limits, at least algebraically, is to cancel and then resubstitute in. And if we take a look at this function, we've got x plus 4 over x plus 4. So that would leave us at 1 over x minus 2. So now, for this new function, we've canceled everything out, but we can. The only value that x cannot be is 2, and luckily, we're asked to evaluate this at negative 4. So we could say that the limit as x approaches negative 4, in this case, will be equal to 1 over negative 4 minus 2. And that is equal to negative 1 over 6. So a technique that you can try if originally direct substitution does not work, if the function happens to be discontinuous at that value, is to factor and then cancel. So we can correctly conclude that this limit is negative 1 over 6. Part C over here is the exact same function, except this time, even if we go ahead and factor out, we still have a problem. So we would have 1 over x minus 2. Again, if you did this whole thing over here on the left, you'd wind up with this setup, and here we could use substitution to evaluate this limit once we've canceled. But over here, if we plug 2 in, we still get division by 0. There's nothing else you can do algebraically with this. And what I'd like to do is I'd like to show you the graph of this so that you can see graphically and visually what is happening at x minus 2 is equal to 0. Now, some of you are probably guessing already that if that factor, it does not have the same factor in the numerator, that it's definitely not going to be a point discontinuity or whole, but it will be a vertical asymptote. So we're going to see what's happening as we graph this, hopefully sometime soon if I can type this into the calculator. And we're expecting something weird to be happening here when x is 2. If we take a look at the graph, and I'll just draw a real quick graph for you over here so you can see it maybe a little bit better. At x is equal to 2, there happens to be an asymptote. So this graph will look something about like this. Whoops, that graph will not cross that asymptote, but get close to it. So there's this imaginary line here, right there, where the graph will get close to it, but won't exactly cross it. The left-hand limit is negative infinity. The right-hand limit is positive infinity. Now I can write that notation for you. That'd probably be a good idea. So the limit as x approaches 2 from the left of this function, let's just name it f of x, is equal to negative infinity. Or some people would say that the limit does not exist because the function continues without bound. There is no limit. However, if you use that notation, you should be okay. And also we could write the limit as x approaches 2 from the right goes to infinity. And for us to conclude something about the limit as x approaches 2, the limit from the left and the right have to exist, or excuse me, have to agree. And so the limit as x approaches 2 of this function does not exist. Limit from the left and the right is not the same.